Energy.
Strong communities.
Buildings.
Security.
Energy.
Buildings.
Conservation.
Durability. Reliability.
Energy.
Conservation.
Energy.
As architects, we grew up and were trained with the idea that form follows function. That somehow the building developed out of the programmatic needs of the requirements of the function of the building. And there was a direct relationship between how the building looked and what it was intended to do. In addition to function, there is a relationship between form and energy.
Primary energy use in America is often divided into 3 or 4 pie segments. There's transportation, there's industry, and then there's buildings, which can be subdivided into commercial buildings and housing. And all buildings represent between 40 and 50% of primary energy use if you include commercial buildings.
My first exposure to the idea of passive house came through a New York Times article that was written in December of 2008. No furnace, but heat aplenty. I thought, a house without a furnace, that doesn't sound possible. There was an idea out there that you actually could create a building without a conventional heating system. That to me is a fundamentally different way of thinking about a building.
We're still building very mediocre houses, which are built based on the energy and environmental thinking of a quarter century ago.
I think that we've, just come through a long period, really 10,000 years, where we haven't had to think that much about the natural world, about the background. It's operated with great stability, and that's let us do all the other things that we've done as a civilization. But the world we're moving into now, clearly that background is becoming foreground. It's that quick deterioration of the physical systems on which we depend.
With nothing but roads and great big 1 acre, 2 acre lots with nothing growing except ornamental trees and lawns that are filled with nitrogen or whatever it is they put on them. That is really wasteful from transportation, from building, layout, et cetera, et cetera. When people travel around in their individual cars and go in and out of the garage to the shopping mall, they don't interact with neighbors. And so there's a huge community disintegration.
It's pretty clear that there's no amount of money on earth capable of dealing with the kind of disruption that is coming at us unless we make this transition away from fossil fuel really fast. Nicholas Stern, the British economist, reckoned a couple of years ago that we were looking at a bill from climate change greater than World War I, World War II, and the Great Depression combined. And we get some sense that that's probably an underestimate just by looking at 1 year's toll of damage from things like floods in Pakistan and fires across Russia and the increased price of grain and on and on and on. Not being too enmeshed in that larger economy is probably a very smart thing right now.
Physics is in some way the science of energy. So we have looked into the potential alternatives, what could be done in the future to secure our style of living in a future where we've already known that fossil fuels will be much more expensive and that they have certain implications for the whole system on Earth.
To understand who he was, you have to go back to another time, when the world was powered by the black fuel, and the deserts sprouted great cities of pipe and steel. Without fuel, they were nothing. They'd built a house of straw. The thundering machine sputtered and stopped.
I don't believe that we'll be able to avoid climate change. I think if we were to somehow be able to turn off carbon emissions tomorrow, magically at the flip of a switch, we would still see the atmosphere change, and we would see the global climate warm to some extent. And we need to prepare for that.
When we were kids growing up, we were just always taught to save things, conserve things, not to waste things. And so I sort of approach energy in houses from that standpoint.
If we imagine this as being a graph, we could think about the energy timeline of this country.
The availability of materials for a building was dramatically restricted by how much you could carry, how far you could carry a log or a stick, or how long a horse could drag a cart with stone on it. So materials were by necessity very locally based.
So the first value you see is wood. Wood was plentiful in North America. The settlers, when they arrived, used wood to build their houses. And if we think about the buildings that were built during that period, we think of a very simple gable form with a big chimney and very small windows and probably a door. One takes for granted that we have electricity that can power lights. One takes for granted that we have fuel that can provide heating and cooling. If you remove some of those pieces from the equation, it's interesting to think about how our built environment would have to change.
We would be so much better as a nation if we've become so wasteful. I see it in everything. I mean, we see the obvious things, packaging, and we see gas consumption, and we see that when our gas bill gets high, when we fill our car. How much do we allow to be wasted that doesn't directly impact us because we don't see the expense of it?
100 years later, when we look at that timeline, wood is still the predominant energy source for the country. And the buildings look very similar in a world where the only ability to harness energy is through that which your body or an animal can produce, and the only materials really available to you are wood, that you're going to make something fairly simple in shape and in form. What I love about this building and all the buildings in the national park out in Concord, Massachusetts, is there are several salt box houses, and all of them have the large facade facing south. And somewhere in the early part of the 19th century, a new fuel source emerges. And this is coal, the dawn of the Industrial Revolution, and fossil fuels are discovered. So in the second half of the 19th century, Victorian buildings. And you'll find them throughout America, whether it's in Massachusetts or San Francisco. We have a new style of architecture that emerges. And that is one that is not founded in these very simple forms built around a central chimney, but is generated by very complex shapes which kind of move out in various directions. So gone is the simple geometry of the earlier buildings. To heat this building, it's no longer being heated with a central fireplace. We can now heat hot water, and that hot water can be piped around the building and be distributed that way. So the requirement for the building geometry to respond to the heat delivery system is removed. The other thing about these buildings is, you'll notice on them, is they have a lot of ornament on them. So with our ability to harness the energy from coal, we can now make 100 of these, and we can place them all over the building. So we really have, for the first time in this country, a style of architecture which kind of detaches itself from place and begins to move across the country independent of climate. In the 20th century, new fuel sources are discovered, and one of them is petroleum. If we think about the buildings that grew up during that period in a very fossil fuel-rich era, one of the most notable buildings is the Farnsworth House, designed by Mies van der Rohe in Plano, Illinois in 1951. This building is a building made entirely out of steel and glass in a northern state like Illinois. Given the abundance of fossil fuel energy available at that time, You could literally have a building that not only defies gravity in the cantilevers and the steel structure, but also defies the local climate. Because with enough energy, one can keep this house relatively warm and relatively cool in the summer. What's interesting about this building, when you see it in photographs, is you never see the large mechanical system that sits on top of the roof. People began to question the idea of unlimited growth. There was also a very significant event, the 1973 OPEC oil embargo. In the 1970s, a whole new idea about buildings began to emerge.
I got involved with passive solar architecture in the 70s. And passive solar architecture was focused on the resource of the sun being used by the architecture.
And during that period, there's a whole history in North America of buildings being built throughout the country that were responding to problems with fossil fuel energy and the idea that we couldn't continue on this path forever. So those buildings, there are a couple of notable ones. There's one in particular that was built at the University of Illinois in Champaign-Urbana. They dubbed that house the low-cal house for low-calorie. And it was a very simple building that really relied on very thick walls. So one of the very early super-insulated walls, it had your classic double stud wall filled with insulation, triple pane windows.
Everyone remembers a hot pot for a coffee carafe. You know, here's the handle and then the coffee is in here. And as long as the electricity is working, the heat is constantly moving into the coffee. The coffee is warm only as long as it stays on the hot pot. But today, what you find are not hot plates, but thermoses. So if I can just sort of imagine a thermos, and the coffee is kept warm, and its heat stays inside the carafe. There is no heat leaving the carafe. That is the sort of model that we think of as for houses today.
As the energy context began to change, so too did the architecture. Unfortunately, by 1980, the oil embargo was long forgotten, and the policies of this country changed in such a way that energy prices didn't continue to increase, but they plummeted. And that resulted in, at the close of the 20th century, what many call McMansion. So the size, the materials they were made with, where they were located, were clearly reflected in this abundant amount of energy, of cheap energy, that we had available to us. How will our built environment begin to be shaped around this new energy context of the 21st century? Can we expect buildings to be scattered out on the periphery away from public transportation and services?
Because our lifestyle, our entire civilization at the moment is based not on manpower, not on animal power, but based on oil power.
We've been very cavalier about how we've used energy over the last several decades.
Oh! Excuse me, Mrs. Schwartz, could you tell us how you feel about oil heat?
Oil heat? Oh, well, I think oil heat is wonderful. See, I'm showering in this delightful hot water. All I want, all I can use. And I know for a fact that only oil heat can give me so much, so fast, and it's so dependable. And I got my dishwasher going, my washer going. Still plenty of hot water. Whoops, I dropped myself.
I wouldn't say that we've had the wool pulled over our eyes. We pull it over our own eyes. We either have to drastically change the way we build buildings, the physical buildings have to change, and the whole structure of our industry has to change, which is the harder part. And if that isn't done, the only alternative is to shoot the people who are living on top of the sand that our oil is underneath. So when you look at these options, there's a lot of reasons to do a lot of wool pulling.
It's an abstraction for a lot of people, and as are many things. I mean, politics is for many people an abstraction. What's happening now in the Middle East for a lot of Americans who are trying to make ends meet is an abstraction. The melting ice caps is an abstraction. So, our struggle is to kind of connect the problem that we're facing in global warming with the everyday lives of ordinary people.
It is indeed possible that we can, in fact, turn our energy pyramid upside down. Right now, the big base is coal and oil and gas, and renewables are really just a tiny little tip. We can do it exactly the other way around: coal, tiny little tip, and then renewables, and above renewables, even conservation. And this is where the buildings come in.
The Passive House Energy Standard relies on a super insulated, nearly airtight, passive solar designed building with a heat recovery ventilation system, and no detail, regardless of how small it is ignored. So everything from glazing percentages to the shading around those windows to the type of insulation used and where it's used, all those are factored in and are tied to a specific heat demand and air leakage standard that needs to be met.
What distinguishes the 21st century house from our point of view is not the style, not what it looks like from the outside, but rather how it functions. These three buildings, each of them are very much part of their time.
Passive House explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist, Dr. Feist, built the first passive house. Here's what he did. 1. Proper insulation. It's just like wearing the right winter jacket, it also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out.
If you in your house burn less fossil fuel, which is coming from out of the country, then that less amount you burn, that less amount of money you spend going out of the country is money that stays in the state, in the country, in the region, and is available for the economy to create and hold jobs.
The really big thing is to reduce our loads to the extent that we can, both heating and cooling loads and, plug loads as well. But the greenest watt is the watt not used, right, or the negawatt. So in an even slimmer, thinner market, that people are looking for a market advantage, and I think that a really intelligent energy design provides just that.
Our old house, my son's room, was boiling hot in the summer. It was freezing cold in the winter. We were always futzing with thermostats and trying to regulate heat upstairs, heat downstairs, cool upstairs, cool downstairs. It was painful.
Our previous house, I would wake up in the morning, I would wake up cold, and I'd get in the shower and I'd get out and I'd be cold, and I'd run around the house and I had my thick sweater on, and then I'd get in the car. Here, I wake up, I put on my t-shirt, I'm not cold. By the time I actually get into my car, I've been running around so much with the normal getting kids ready for school, getting breakfast, whatever, that I'm practically sweating by the time I get in my car. And I'm never cold.
If the goal is to build a zero-energy home, this appears to be the most cost-effective way to reduce the size of that renewable energy system that the homeowner would later invest in to get to zero energy.
Dealing with all the things that you deal with a normal house, when you know that 90% of those can disappear if you put a little more thought and a little more attention into the engineering of the house. You have a house that's really comfortable, that you really enjoy, that you can stay in for the rest of your life, and that you don't want to leave. I don't know if I can say that for any other houses I've ever lived in.
It doesn't make any sense not to build a passive house, just because, especially in an environment like this in Oregon, where we have some hot, we have some very cold, and it makes it really comfortable all year round without any effort on our part. And in the long run, it just makes a lot of sense financially and physically.
One of the critical pieces of successfully building a home to this type of energy standard, such as Passive House, is to have an integrated design process. That is, before we've even begun construction, we are having design sessions with all the members of the project team. That would include the builder, the homeowner or building owner, the passive house consultant, the electrician, the HVAC consultant. They all need to be there, and we all need to be discussing the strategies we are going to be achieving and make sure that everybody's on board and clear on the goals. Once we've done that and construction starts, it makes everything flow more smoothly. If you've already talked about the way your ventilation system is going to be ducted and allocated spaces in your wall cavities for those ducts, then when it comes to rough-in, there are spaces allocated for those, and contractors aren't having arguments in the field or showing up and their bay has been taken by another contractor.
How big are these units, you know, when we stack them together?
Probably the best thing to do is bring them down here. They're in the car.
Well, about.
Yeah, well, you're going to be the width.
Because I just want to lay it out over here. My feeling is if we don't take our space, somebody else is going to get it.
The Passive House Energy Standard has a very strict air leakage standard. And to achieve that air leakage standard, one needs to conduct a number of blower door tests where basically we're simulating a 20 to 25 mile an hour wind on all sides of the houses at the same time by depressurizing the conditioned living space. In doing this, we're identifying where air is leaking into the house. We can couple that with an infrared camera that can actually identify exactly where those air leakage are coming in.
Now darker represents cold. So you can see we have 50-degree surface temperature there because we got a little bypass in the corner.
Typical build, you would be able to see every stud in the wall. I'm going to assume that the roof system is sitting at these points. You can almost just see a little conduction every 24 inches. We can also do theatrical fog tests where we'll fill the space with fog, pressurize the building, and actually watch as the air leaks to the outside, which is where the fog or smoke is coming out of the house. Those types of performance testings can really help identify exactly where you should be spending your efforts, as opposed to assuming that if you spray foam or caulk this area or air seal this area, and you may be actually missing some of the larger leaks or maybe some of the smaller leaks that are critical. And in doing that, you're also ensuring better durability for that envelope. If we've missed a significant air leak because we haven't conducted the performance testing, then we may have potential mold and mildew issues down the road.
One of the principal fears that people have is this building being very tight. And over the course of my career, I've really seen that breathing in a building means a building's ability to be able to manage moisture. And that when people start to understand that a building breathing, meaning it being leaky, is actually an unhealthy thing for them and an energy waste, then they start to get on board with the fact that, you know, we can build a tight building and we manage ventilation so that people actually have fresher air and a more comfortable environment than they would have if the building was leaky.
Your warm air is rising up to your attic spaces, up where there's this positive pressure plane. And inevitably, that area is going to have leakage. And what happens when that air leaves, air has to come in. And so the negative pressure plane, where it's demanding more air to replace the warm air that's leaving up top, is coming in down low. And typically that's around the basement ceiling, where you have your band joist that wraps around the house, where you have a lot of lumber stacked on top of each other, penetrations where your boiler may be venting, or your electrical main panel's line is going out to your meter on the wall. All those are penetrations where this cold air during the heating season can just come in.
After we bedded the plywood in the joint and seam filler, we come back on the face and do a swath of joint and seam filler, and it's completely air sealed. We've got this big long cantilever, we've got a pipe penetration, everything's detailed out. If you were using a peel and stick, you would have a lot of joints right here. So we're completely air sealed, and we're water sealed. Pipe penetration, we just cut the hole really tight, and then we can come back with joint and seam filler and cut in the whole way around the pipe, making that penetration completely air sealed. With most other flashings, you would have to leave an opening here that you would have to come back and detail in, and it would be several different pieces of material tied in with each other. Here, when we pull this out, we just roll on more Cat 5, and it just blends in completely seamlessly.
Air will move in and out of the building when there's a temperature difference between the interior of the building and the outdoors. That's just physics. We can't stop that, but we can close up the holes. Once you can control the air, you can create a lot of good comfort, and you can start to address air quality.
If you walk into a passive house building, and I've been fortunate enough to be in a few now, the air is fantastic. You're getting great air exchange. You're getting air brought to where you want it to be instead of through cracks and just showing up and wherever it ends up leaking into a building. You also have, because of the air tightness of the building, an incredible sense of security. You have soundproofing. It's really a very beautiful type of environment that's created.
These homes are not only extremely comfortable because of the great temperature consistency throughout the house, but they also acoustically are very quiet.
First of all, fiberglass is very easy for air to flow through. It's what they make furnace filters out of for a reason, because it's very air permeable, as opposed to the dense packed cellulose, which is very air impermeable and very resistant to air movement going through it. This demonstration is just going to show you some of the sound characteristics. So that has some effect on quieting it down. As opposed to the cellulose.
There are almost no temperature differences inside of the buildings. There are no drafts, there is no noise. It's much easier to reduce noise if the airflow you need is lower. And so in a building which is not very well insulated, I've seen there are single panes still here in the windows, you need quite a big amount of heat or cooling energy to keep it in a comfortable range. And even here, I can feel the draft. I don't know whether you can feel it. I can feel the draft in here. So even this is a equipment which tries to give you a comfortable condition here, and it creates a draft. So that's...
It's not about improving energy efficiency incrementally, a little bit. There's a lot of technical and economic arguments that can be made. Let's just go very far. If we had competitions for energy use, everybody would be building buildings that would look like passive house buildings, technically and physically. That's where we would be at. So the passive house standard is really ingenious to just jump us over there. It doesn't pay to go part way there. You get some of the benefits and a lot of the costs. And the cost-benefit ratio, they found a sweet spot with the passive house.
This system, this pump, is directly connected to our HRV unit. There's a temperature sensor in the incoming fresh air. And when the temperature goes below a certain degree, this pump kicks on and it starts drawing glycol from tubing around our footing that's in contact with the undisturbed earth. It draws that glycol into a copper coil that's behind this box here. And the fresh air comes through that copper coil. That copper coil is about 50 degrees Fahrenheit year-round. And as that air comes through that 50-degree coil during the heating season, it actually preheats the air. So if we have 10-degree air coming into the unit, it will go through this 50-degree copper coil and it'll bring it up 35 to 40 degrees. In the summertime, on the reverse, that warm, humid air from outside, that comes through the 50-degree copper coil, but it also cools that air before it's delivered to our HRV and hence to the house. So this acts as both a preheating and a pre-cooling system. So what we're seeing is, we may have 10-degree air coming into this unit, but as a result of our soil heat exchanger here, this water-to-air coil that preheats the air before it comes into the HRV, we are seeing only a couple degree temperature drop in the supply air, which we're getting from the outside, when compared to the set point temperature in the house. So if we're, have the set point at 70 degrees in the house, this cold air coming in is going to be delivered to the room around 68 degrees.
The future of energy, I think it's going to be based on conservation and renewables, passive houses, which will empower the individual and access for them that invisible oil field that we call energy savings.
Most of the highly industrial materials that we often associate with modern construction, that is contemporary construction, are like glass and steel are actually more 20th century materials because they are very, very high carbon footprint.
A good passive home also concerns itself with the choice of the materials that it's made out of, because if we have lots of embodied energy in the now increased insulation and wall thickness, then we're kind of defying the purpose. So we should choose materials of low embodied energy that have high insulative values, and I would say cellulose is hard to beat.
Cellulose won't burn.
Passive housing is one proven way of achieving houses which use very, very little energy, as little as 1/10 of a conventional house. And passive design concepts can also be applied for retrofitting existing housing to drastically reduce the heating and energy requirement to a fraction of what was the case before.
We are at our brownstone renovation located in the historic district of Brooklyn Heights. We're bringing it up to passive house, future-oriented building energy standard. Basically, the trick was to maintain the historic fabric of the house, the brick facade, and historic detail on the outside, bring the interior up to date. For better or worse, the house had previously been poorly renovated. There wasn't a lot of historical detail on the inside of the house. We are not permitted to insulate on the outside of the brick structure. The cellulose here, which is blown in dense pack on the inside face of the brick wall between wood studs, and then we sheetrock over the dense pack cellulose.
Insulation never breaks. The investment you've made in the envelope will be there for the life of the building.
We're frightened of, builders that tell us, oh, this is what you should do, this is the hot new thing. The big advantage with this is not only can we model it ahead of time, now we have the statistics to show, yes, that's what we said it would do, and it's doing exactly that, or even better in some cases.
We're going to be installing insulated glass panels where the old glass was, and we're going to be putting a 5-point lock system to crank it down and lock it in for the airtightness. A lot of times where you have freestanding buildings, you're looking to orient the building to maximize the solar heat gain. In New York City, we're locked in, and we have no choice. This house is oriented east-west. These windows here are some of the only windows we have facing south. The housing stock is typically row houses where we have party walls on both sides, so we don't need as much solar heat gain. And we don't need as much insulation on the buildings either. We're not allowed to have double-hung windows in a high-performance building. To make them perform over time, you would need to nail them shut and caulk them shut. They're going to come apart and leak air, if not on day one, on day 2 and 3. And with the weight of the triple glazing, they become fairly impractical. What we wanted to do is simulate the look of the double-hung to meet Landmark's requirements and maintain the high performance of the building. And so what we have here is a window that looks from the outside and even from the inside when it's closed like a double hung, but operates like a tilt turn on the bottom half, and the upper half is fixed.
Windows are the hole in very good envelopes, and the hole goes both directions. The hole lets heat from the house out, but the hole also lets sun in the winter, and we could cover up to 35% of our heating demand with the passive solar gain of sun rays coming through glass, heating the interior of the house. You should be able to get a net zero element. That's to say there should be as much heat gain as heat loss over the heating season. You can't do that with a wall. So the windows are pretty magical elements. Get it wrong and you have a terrible burden for your energy balance. Get it right and it's an asset.
The best windows will be more energy efficient than the walls around them. If you build a passive house envelope and forget to put in the windows, and then remember the next time and you put in good windows, the house with windows will use less energy than the house without windows.
sort of traditional air handler for air conditioning. The difference is that if we were building a typical house here, the air conditioning system would be about 12 tons. And with this house, we're figuring about a little under 2. At the perimeter here, under the windows, we would typically have baseboard heating, and we would have ducting bringing the air conditioning to the perimeter of the house. But because it's a passive house, the heating and air conditioning is delivered at the interior side, allowing us to have much shorter duct runs, and is part of the cost savings in the initial construction. The guts. We just have a quick look here. You can see one of the nice things about this ventilation system is that in many ways it's plug and play. This is a distribution box here, either the supply air or the return air. And on the other side, you have then the branch ducts going out to all the different rooms. We have the good fortune here of having an attic space that was actually usable. As initially built and as the previous owners had used it, the attic space was just storage space. But we took the opportunity of the renovation to activate it as a family room and open it up completely. A lot of the houses that have been renovated have a lot of mechanical equipment in this space. And in fact, the previous owners had ductwork and huge mechanical equipment all in here. But because our mechanical equipment is 1/10 of the size, it allowed us to stick it in relatively discrete closets downstairs and really take advantage of the space. They didn't have to put 5 tons of air conditioning just for this space because it wasn't going to be a broiler in August. We had these thermometers installed after the middle of winter when it was extremely cold in New York. We had one particular weekend where it was 0 degrees out. Monday morning, when the workers came in, the house had been completely unoccupied over the weekend. No lights, no tools, no heat whatsoever. 8 degrees outside Monday morning, they come in and the temperature was just over 50 degrees inside the house.
But it costs too much to build passive is a question of too much compared to what?
Well, in fact, there is some additional upfront cost, especially if the designer is doing it for the first time, the builder is doing it for the first time. But we've seen in Europe and also here now in our 7th project that as you go through the details very diligently, you're really able to optimize, you're able to think a little bit differently and save here and there. And we're building houses right now for under 10% additional cost, which is a payback of between like 7 to 11 years, depending on size of the house or building.
We really try to explain to our customers that there is value in not necessarily going the cheapest or the blitziest path. I always call it icing the cake, you know. Every wedding cake is still a yellow cake by itself underneath all the stuff on it. So there's a balance between the stuff we put on the house and the stoutness of the core of the house, the cake itself.
We found that the additional cost a homeowner will incur on a monthly basis with his mortgage would be more than offset by the savings in energy cost. On about a 2,000 square foot passive house may increase by about $100 to $150. But the energy savings we're seeing for that same space would be around, and this is at today's energy costs, around $300 a month. So on a monthly basis, we'd be saving about $150.
We're seeing energy savings that are on a par with the additional cost to build a high-performance home. Financing lets you spread out the additional burden of building a high-performance home. And when you spread it out over time, that's just what's happening with your energy costs. Your energy costs are spread out over time, and so they can balance each other out.
Clearly, the overwhelming need is to address the threat of global warming. But the elegance of having a good thermal envelope in order to reduce your energy use makes clear and obvious sense just from a cost-effectiveness standpoint.
People's homes mean a great deal to them. They represent safety, a hope for the future, and really most of our most closely held values are somehow manifested in the home. But it's competing with an idea that we all want to bargain.
Anybody whose economic strategy relies on the fact that the economy is going to keep growing and growing and growing may be in for some surprises. It's going to be harder and harder to grow our economies, I think, especially as we begin to run short of oil and other things. Not being too enmeshed in that larger economy is probably a very smart thing right now.
Education is key, not only with consumers, homeowners, home buyers, businesses, people that are looking for new buildings, but also for the profession. And the building industry, by its nature, is very conservative. I can't tell you how many builders I talk to who say, well, this is the way my grandfather did it, and his houses didn't fall down, and it's the way I'm going to do it. There's a lot of resistance to change. Yet at the same time, we need to change. We need to make pretty dramatic changes, and we need to do it very quickly. Still, a lot of the building industry doesn't recognize the need to maintain their education throughout their career.
This is an ancient practice, and it takes a long time to catch up on all kinds of aspects of the design of a building. There is fear-mongering due to ignorance, but there's also a lot of successes out there and a lot of really good examples of how a holistic approach to building can actually create something that's safer, healthier, more energy efficient, and more durable.
What we lack, unfortunately, is a code enforcement mechanism, and that's where it all falls down. Changing the code won't work if it's not enforced, and there are plenty of research studies that have definitively proven that the existing energy code is not now enforced and never has been. So it's a code, but it's a code. So how do builders really want code enforcement? No, they don't. It's not as if, the code is a sham. We just haven't focused on energy efficiency. So builders need to learn to build a house that performs well in a future with rising energy prices.
The Passive House Energy Standard is a giant leap from where we are currently in regards to designing and constructing our buildings. And as a result, inevitably there is a very sharp learning curve to get to the air leakage standard, the type of thermal envelope, and actually the type of building designs. Unfortunately, our designers, our architects, their aesthetics are disconnected from the actual performance of the house. And so what we're looking to do is align those two, find a balance.
Right now, the way the construction industry is set up, nobody involved has the power to make a building energy efficient, or safe, or healthy, or comfortable. The architect can. The builder can. None of the subcontractors can. The owner can. As a group, these people can. But my industry is set up with islands of liability, which are not shared. So everybody wants to make sure their piece is done and no problems creep over from any other island.
If we're moving to a different type of framing system, going from your typical 16 on center framing with solid headers to advanced framing that requires 24-inch on center studs, a little bit wider spacing, and insulated headers over your windows and 2 stud corners. A lot of builders are very resistant to that because ultimately it's not something they tried. But what we found is that actually advanced framing significantly improves an envelope. It reduces the amount of wood in a wall while not compromising the structural integrity and allows for a great deal more insulation to get into that wall.
I picture a future where everybody on the construction team is sitting around the table talking about how can we get the heating and cooling and ventilation equipment, or smallify the heating and cooling and make the ventilation system more efficient. Well, first finger would be pointed at the engineer. Give us a smaller heating system. And the engineer would say, well, I don't know how well that wall's going to be insulated, and I don't see anything on the blueprints that shows me how that window is going to get installed in that wall. I see a good window, maybe somebody budgeted for a very good window. Maybe there's a lot of insulation in the wall. But where's the connection detail? The architects reduce their liability by not putting that detail on the plans. So if it's done wrong, not their problem. So everybody would point the finger at the architect and say, show a good detail with a good air barrier so we don't have air leaking around the window. Air leaking around the window, of course, makes the place humid in the summer, cold and dry in the winter, uncomfortable all year round, and not only does it waste energy, but then the energy use is impossible to predict, so you have to oversize your equipment for the load, plus the I don't know how big it is load. So if you put an air barrier, your system gets smaller, the building is cheaper to build because the air barrier is cheaper to buy than the mechanical equipment. Hallelujah, a cheaper building that's more comfortable, more healthy, and performs better. It's not more money that we need, it's more knowledge, and we need to change the relationships between the people on the team.
In a way, it's easier to build an uninsulated home than an insulated home because uninsulated homes stay dry and they may waste a lot of energy, but they aren't as susceptible to moisture damage. In other words, if you go halfway towards an energy efficient house, you can get to dangerous territory pretty quick.
And the building itself is a kind of dynamic entity. You know, it's gaining energy and losing energy in different ways in different places. Well, if you choose to lose a lot of energy with this one component, realize you got to make it up somewhere else. To achieve that balance, one needs a completely integrated building in terms of the systems, the wall, the windows, the insulation specifications, etc. Typically, one can't arrive at something so integrated just with one person.
How small is the heating system? How small is the cooling system? How much energy does the ventilation system use at peak? So you add up the peak energy input, source energy input to these systems, divide by the square footage of the building, and that's the best proxy for energy use that anyone can come up with. Fancy computer modeling, maybe somebody at NASA can do something better for one or two buildings. But in terms of something that can be adopted by our industry as a whole, verified by a building inspector at the blueprint stage, at the construction stage or later, this is bulletproof.
I feel like this is a culmination of 40 years of building learning on my part, and it's finally getting back to a fairly simple process.
Ultimately, what we're finding with the Passive House Energy Standard is it helps guide the design. You take this specific detail of a home, and if you modify it, you're going to know exactly the impact that's going to have on the heat demand or the cooling demand. How many more BTUs per square foot you're going to require on an annual basis to take in those views. And if you do want to do that, then you're going to have to fool around with other parts of the building to offset that.
My name's J.B. Clancy. I was the architect for this passive house for Habitat for Humanity. This is the first passive house I've designed, and it will also be the first modular-built passive house in the country.
When we build a wall, the first thing we do is sheetrock it, then we start framing it, which may seem a little strange, but we build our wall laying flat on a work table. Then we put our sheetrock on the table, we frame on top of it, and we come in and we spray a foam adhesive onto the sheetrock wall, sheetrock stud, and that does two things for us. The first thing it does is it attaches the drywall to the framing. Second thing it does is it gives me a complete air seal. So all our sheetrock goes out of here, airtight drywall. We also use finger joint studs. Then we install a cellulose insulation.
Clearly, the modular build was exciting from a delivery standpoint. I mean, at 8 o'clock in the morning, there's nothing but a foundation there and a clear open field behind. And within a few hours, in comes this house and put together like a great big puzzle.
We don't want to depend on our modeling of the Habitat for Humanity house. We don't want to depend on energy modeling for any of our buildings. We really want to verify that the performance standards that we are intending to meet are actually being met. And as a result, we're incorporating a fairly significant monitoring system into our initial houses here to demonstrate and verify that the energy savings claims, the indoor air quality claims, and the comfort claims are indeed being met. We stepped into the passive house, Habitat for Humanity house in Charlotte, and it was 15 degrees outside. It was 4 degrees with the wind chill. The sun hadn't been out in a couple of days. And we have one little electric heater plugged into the wall and found that throughout the house, we were keeping a temperature of around 62 degrees Fahrenheit. So with one little point source heater located in the main living room, it was keeping the first floor bedroom and bathroom, the two bedrooms on the second floor and the bathroom, all at the same temperature. And this is with really harsh conditions outside and without factoring in passive solar gains. The reason that we pursued modular with this specific Habitat for Humanity project is so we could create a package, so to speak, that could be replicated anywhere. And
we have found that that indeed has brought a lot of prospective builders to the table.
The idea that there is a package out there that they could buy, build in 2 weeks, set and deliver in 5 hours is something that is really attractive to not only the builders out there who could turn around a project in a fraction of the time that they typically would, but to homeowners that are looking to transition into a new home quicker than the typical 6 months that it takes to build a new home.
I feel like we're on a dawn of maybe through passive house construction to see a simplification of what houses are.
The building itself, the envelope of the building, is the primary mechanical system. The other systems are serving in support of that.
And how can we reduce what we need in the house instead of thinking about exotic ways to just make more and more energy? It goes back to the men in the field and the carpenter and the assembly process.
Really, why do we design any shelter? It's to protect us from the elements, probably one. And two, to provide a comfortable environment in which to live. And if that's the primary goal of a building to begin with, rather than rely on equipment, we can actually now turn to the building itself.
But if somebody calls me tomorrow and says, I want to build a 10,000 square foot house, I'm going to be the guy. I mean, yes is my answer, because they're my customer, and that's where, that's what makes custom builders build for their customer. That doesn't prohibit me, though, from pontificating and trying to change their perception of that house. My first question is going to be, do we really need all this space? Or are you just picking a number because it ended in a certain amount of zeros? We're in business to do what customers want us to do, and we listen to them. We hope they listen to us. And so our impact doesn't come on the customer walks in, wants a 10,000 square foot house, and we convince him to live in a teepee that's well insulated.
So the current situation with passive housing, I would say, is in early adoption. We have a lot of very enthusiastic people, and the ball is beginning to roll. And like any ball rolling downhill, it's just going to roll faster and faster and faster and faster.
Ideas like the passive house are really impressive and important because A, they help us deal with our fossil fuel dependence and get some carbon out of the atmosphere and things, but B, they provide the example of the ways in which we can get the things that we want from the world: warmth, shelter, a kind of security, without having to have this constant dependence on unsustainable things around us. It's really quite a beautiful psychological idea as well as a physical one.
We're interested in fewer moving parts, more responsive to the atmosphere, to the climate, to the sun.
You don't design the building and then say, oh, by the way, could you give me an energy rating on this building? You begin with an idea, and then you bring an energy model along with it to test that idea. And through that dialogue, that's kind of how the form follows energy part. As the design is being developed, an energy model is also being brought along with it. And those two inform each other.
The passive house is an example of how we can become much more energy efficient in how we conduct our lives.
So with this idea that we are inevitably going to be seeing significant energy cost escalation in the future, why wouldn't you invest in this right now?
We live in interesting times, and we are going to make important changes in the way we live and the way we build houses, whether we want to or not. But the timeline is so short that, we're going to have a shock to the system one way or another. Choose your shock, Is it going to be a political shock, or is it going to simply be a disaster shock?
We need buildings that that don't contribute to the problems that we face and can withstand the damage that we can no longer prevent.
What the 21st century architecture should be is not about style, but today we think that the main issue is energy.
It's pretty clear that there's no amount of money on earth capable of dealing with the kind of disruption that is coming at us unless we make this transition away from fossil fuel really fast. All we can do now is keep it from becoming any worse than it has to get. The climatologists are clear that the temperature will go up 4 or 5 degrees if we don't get our act together very, very fast. That's what this century is going to be about.